These are the two textbooks I'm using. I don't even know if they've got them in the library. If anyone wanted them, I can bring mine in, but it's just so that you guys know what I'm working from. Okay, as we said on Wednesday, gravity, you're really dealing with Newton's laws. And so you will have learned it before. I hope this isn't too dark. You're dealing with Newton's third law, and it's the fact that you have two objects, they will attract each other. They exert a force on each other. And this force F is equal to G, which is the gravitational constant, times by the mass of the one object, the mass of the object divided by r squared. And so r squared obviously is the distance between them. You can see that in the figure here. You would have learned it in class with normal masses, but now we're actually dealing with a point mass. Because we've got the Earth is the one mass, is m1, and then we on the Earth are so small you can consider us to be a point mass, and you can only assume this if the object is small in comparison to the separation. And so really that just means we are very small compared to the radius of the Earth, because it's the center of the Earth is attracted to our center, and so the distance between us is like 5,000 kilometers, I think is the radius of the Earth. And so that is very, very large compared to this point mass. And so now we're taking that equation and we're adapting it for the Earth. And so we're keeping G, ME is the mass of the Earth, MS is the mass of your small object, RE squared is the radius of the Earth that we just said. And so this can then be combined with Newton's second law. And Newton's second law was that a force is equal to mass times acceleration. And so the mass is the mass of the small object, and the acceleration is g, which is gravity. It's the attraction due to gravity to the Earth. And so we take that equation, we combine it with the one above, and you can just swap stuff around, you bring m to the side, it cancels out, and you land up with this equation. So this is really the equation for the gravitational attraction of an object to the Earth. So you would have in physics, you've learned that G is equal to, is it 9.8 meters per second squared. And so this is the equation to derive that value. And so we're all attracted to the Earth at approximately 9.8 meters per second, but it actually, when you go on the smaller scale, varies slightly, depending what objects you've got. And like we said the other day, if you're doing a gravity survey over normal rock, G will be one value, but if you suddenly then go over a big body of gold, because the gold has got a different density, your G will change slightly. So you've always assumed it was 9.8, but actually it changes slightly. But we only deal with that because our gravimeter, we said the other day when we're doing a survey, the box can actually measure these small changes. Does anyone remember the value? 0.04 can actually measure such small changes in gravity. So that's why you've been saying 9.8, but now we're actually looking in the decimal places at these small changes. And so here you can see we assuming that the Earth is a series of concentric circles, and so the attraction of a uniform sphere is equal to the attraction of all the mass concentrated at its center. So like I've said, we assume all the mass is concentrated at the center of the Earth. There's this little mass there, and they're attracting each other. And G is the same everywhere on its surface when you have a uniform sphere. But we all know that the Earth isn't uniform. It's actually, does anyone know, is the radius more or less at the equator compared to the poles? The equator is more. Poles are less. So it's a bit wider at the equator, and it's a bit squashed in at the poles. So you'll see that on the Earth, not only do you have this change in G, because sometimes you've got normal rock, sometimes you've got gold, sometimes you've got others, but also what latitude are you doing your survey will actually affect your value of G, because the Earth is wider at the equator than at the poles. And this is just for me to remember. We can write it down because we'll probably need it for some equations just now. The mass of the Earth can be calculated, and it's 5.97 times 10 to the 24 kgs. Okay. And actually, let's go back one and write down G. So if you remember to flip through the slides, 6.67408 times 10 to the minus 11 meters cubed, kilograms, 1 s to the minus 2. And we just keep all the units so that you can ultimately figure out that you're using the right units. Okay. Okay, so that's really what we are concentrating on in gravity, is calculating this value or the change in this value from place to place. So these are some of the densities of rocks. And so you've just got to kind of get used to it. You've got to get a feel for it. So I've said there, what trends do we see? So let's look. We've got unconsolidated sediment, so like sand, clay. You've got quite small values, if you can see. 1.5, 1.4, maybe up to 2. So something you can keep in mind, the average density of the Earth, they take as, let me do average density, 2.67 grams per centimeter cubed. Okay, so you can, this is just a benchmark to take from. So you can see these values are quite a bit lower. And it's the fact that it's loose soil, so it's not very dense. Next one we're going on here are sedimentary rocks. So you've got coal stone, sandstone. So it's all the sandy rocks. Again, quite low values. These kind of getting a bit high in here. And you can see there's a range, not just one value. So when you go out into the field, usually what you do is you pick up a rock sample and you make a measurement of it to get a value for your area, because it can be so different. So again, quite low values. Then igneous and metamorphic rocks. So igneous rocks, the rocks that have intruded inside of the earth. The one you'll know most common is granite. And what other ones you know? Basalt is the ones from lava flows. So these are rocks that are linked to magma. And sorry, you can see that they're quite a bit higher. So you're now starting to get values close to 2.67 and over 2.67. And then down here, minerals. So yeah, these are just individual minerals in the rocks that could be mined for iron and copper and all of those, hang a lot higher. But usually you don't find a big lump of them. So on Wednesday, our example, we said we had a big lump of gold. You don't usually find a big lump of gold. And you don't usually find big lumps of these. They're usually small little bits in the rocks. So it is very dense, but it's called disseminated. It's throughout the rock. So it won't be so dense at all. So what trends can you see? Which one has the lowest density? Water, yes. And rock-wise, which ones have the lowest density? Yes. And the next ones? Yes. And then your highest ones were the minerals, yeah. And then next along were your igneous rocks. So yeah, and so you can generally have an idea of what densities you're going to be expecting. So that you don't have to listen to me talk all the time. I have a thing for you guys to solve. So you have to calculate what the value of G is at the North Pole, given G at the equator is this value in meters per second. You'll see that G at the equator is 9.79, but if you calculate it at the poles, it's 9.86, which don't unfortunately fit with any of the answers given, and maybe there was a misprint in the textbook, but this all makes sense because at the poles you're closer to the center of the Earth, so you'd expect G to be bigger, whereas at the equator you're further away, so you'd expect it to be smaller. Okay, why is it more correct to talk about determining the mass of the Earth rather than the weight of the Earth? What is weight equal to? Because weight is a force. So F is equal to ma, and so this is W is equal to mass. What is the acceleration? It's actually gravitational acceleration. So G is what's giving us the weight. There is no G applied to the Earth. The Earth, G is something that we experience standing on the Earth, so the Earth doesn't experience it. So it's much better to talk about the mass of the Earth. So just something to keep in mind. Does a spring balance or a pair of scales measure mass or weight? I found this difficult because I'm not used to using either of them. So think about using them on the Earth and in a spaceship. So this one here is a spring balance. Has anyone used a spring balance before? This one here. You've used it in physics or other things? Physics mainly. So literally you hang the object on here, it pulls down the little pointer and then it indicates what your weight is on here. And this is a pair of scales, and so you literally put, usually I think they used to use it for money and food and stuff in the olden days, and then they had little weights that they put on the other side. And they knew how much those little weights were, and then they would balance out and use that to tell how much gold or food was on the scale. So which of these measures weight and which of these measures mass? It's a tough question, it's a weird question, but it's quite a common question when you're doing gravity. So this one, if we've got a little box here, this one here I would say is weight because it's been pulled downward by gravity. Whereas this one here is not so much dependent on the pull of gravity, but it's a comparison of two objects, and so a comparison of their weight. So, okay, which of the following is not true? The value of G, okay, varies over the surface of the Earth because the densities of the rocks vary laterally, because the surface is not flat, with longitude, with latitude, with distance from the poles. So, think about it for a second and we can discuss each one. Okay. So, for A, is it true that G varies because the densities of rock vary laterally over a horizontal surface? Well, the question is, do rocks change as you walk along? Does the rock type change? Yes or no? Usually, yeah. It might take a while, but it will change. Does a change in rock type cause a change in G? Think about what we did on Wednesday afternoon. When we went over, we had a body of gold. As we went over it, G went up. So G does change. And even we've seen already now that if this was sandstone, or let's actually say this is sand, which had a density of about 2, maximum 2, and this here was granite, which is at 2.67, you've got a change in density here. So that also will result in a change in G. So yeah, G does vary over the surface of the Earth because there's a change in rock type. So now we're trying to find out which of these isn't true. Does G vary because the surface is not flat? So these are all things that when you're in the field, you actually need to take into account. So say you were walking along the surface and the surface is wavy and it's all the same, this is all granite underneath, and you're doing a gravity measurement up here and one down here, and you're constantly up, down, up, down, up, down. And the center of the Earth is down here. Over here, you're slightly further away from the center of the Earth. And here, you're slightly closer. And remember when we were talking about the Earth, at the poles, we were closer at the poles. And at the equator here, we were further away. And we said when you're further away, there's slightly lower gravity. When you're closer, slightly higher gravity. And it's the same with topography, but on a much smaller scale. So here you're slightly further away, so gravity is less. Here you're slightly closer, so gravity is more. So you can see a lot of things affect gravity. It gets quite complicated. So this is actually true because the Earth isn't flat. I want to skip C because, well, it'll give you the answer. Well, let's look here. So with latitude, we've said already, if you're going from the poles to the equator, that's your latitude. So going north to south, there's a change in G. So as you go from the equator, from the poles to the equator, you're getting further away from the center of the Earth, so gravity is decreasing. So there is a change with latitude. With distance from the poles is kind of the same, kind of. So there is. With longitude, there isn't. So that's actually the answer to the question. So as you're going from east to west, you kind of, if you were going to east to west along the equator, you're kind of the same distance from the center of the Earth. Something to keep in mind though, which complicates a bit, going east to west, you're still going over different rock types. So it's the rock types are causing a change in density. It's not the fact that you're going east to west. So this is your one here. With longitude, doesn't affect G, doesn't affect gravity. Okay, another one to calculate. The mean radius of the Earth is 6,371. So I'm going to put that here just so we have it. 6,371. On taking a gravimeter 1 kilometer up in a balloon, you would expect the value of G to decrease by how much of a percent? So you need to calculate G 1 kilometer up. So yeah, you can see that it's a really small change in gravity as you move up in the balloon.
So you can see here that G calculated at the surface of the Earth is 9.816, and then 1 kilometer up, so the radius becomes 6,372, G becomes 9.813. And so if you minus those from each other and calculate it as a percent, you get a 0.03% difference in G as you move 1 kilometer up.
Second last one, calculate the average density of the Earth, given that G is that value, and the average Earth radius is 6371. How does this compare with the density of granite? So I want you to calculate the average density of the Earth. So pretty much using this equation, but then who remembers how do you calculate density? So I struggle to remember equations. So the thing I do is I try and use units. So density is equal to, let's say, kilograms per meters cubed. So obviously then density is equal to mass over volume. Okay. And so what volume are we using? We're using the volume of the Earth, and you can just approximate that the Earth is a sphere. So does anyone remember what the equation for the volume of a sphere is? 4/3, yes, that sounds right. Pi, nice. Pi r cubed. Okay, I suppose what they're wanting you to do is to ignore the fact that you know M. So you're using that equation, you've got G, you've got R, you're getting M. So that means you've got M here, you've got R, you know that value, and so you can calculate densities. Okay, but we're both getting about 5,000. It should be in kilograms. So anything that's in the thousands, just remember it's kilograms. If it's showed it as 5.5, that would be grams per centimeter cubed. But it's, so just try to be thorough when you do your calculations, and I always write the units there as well. Cross out your units so that you know what you're landing up with in the end. You should have been using kilograms because your G value is in kilograms. So does anyone remember what granite was? It was a range of values. I think it was something like 2.2 to 2.7 or 2.9, something like that. And you can see this would have been in grams per centimeter cubed in that table that we had. So it's the same as 2,000 to 2,900 kilograms per meters cubed. So quite a bit of difference. Nothing was really this high except for some of those minerals. And so why do you think this is so much higher than granite? So this was the density of the whole Earth, whereas granite is just the thin crust. So did you go over with Mussett or in other courses, maybe in Geology 1, what else is in the Earth? What makes up the center of the Earth? The core, the outer core and the inner core? Ah, there one. Do you remember at all what was the composition of the core? No pressure tonight. Yes? Iron. Iron, yeah. So like a lot of the Earth is actually iron, which has got a very high density. Pyrite is an iron sulfide, so it's got a lot of iron in it, and it's got a density of about 5,000. So it's this iron that's adding a hell of a lot of density to the average density of the Earth. Explain why portions, so I think like food portions or anything like that, weighed on the high Tibetan plateau would be larger than portions weighed at sea level if they weighed using a spring balance. So it's going back to the thing we did earlier. So the spring balance was the one that pulled down and measured weight. So why would portions on the plateau be larger than portions at sea level? So you're on top of the high plateau, G is less. So your weight of the object is less. So if I've got this much food, it's going to weigh 2. And if I go to sea level, this much food is going to weigh 5. But I want to give you 5 grams or 5 kilograms of food. Therefore, when I'm on the plateau and it's so small, I have to add more food on. So it's actually the portion, so the size of the food, you're getting more food when you're on the plateau because you have to add more food to get to that value of 5, whereas down here it's less. So yeah, so it's actually saying y is the amount of food, not the weight of the food. Okay, the radius of Mars is that, 3,000, and its mass is 0.1 that of the Earth. The value at its surface will give the value of g at its surface. So the radius is less than the Earth, its mass is only 0.1. This is kind of like saying it's 10%, isn't it? 1, 2. It's 10% of the Earth's mass. So what is the value of g at its surface? Have you got a value? How much? I'll show you right. Yeah. Cool. So you can see it's like almost a third of what it is on Earth. Okay, and then a similar question about the moon. So I'll give you the answer. So compared to the Earth, the moon has about the mass of the Earth, of the moon, is about 1/80th, so much less, and the radius is 1/4. How does the surface gravity compare? I've got a value here. It's about 20% of the Earth's gravity. So it's about 1/5 of the Earth's gravity. So quite a bit less. Does everyone know that the moon used to be a chunk of the Earth so the Earth was hit by a meteorite, and a chunk of the Earth got pulled off and then went into orbit around the Earth. So they've determined this because the rocks on the moon are very similar to Earth and magnetic. So as we said on Wednesday, the main thing that gravity that you're looking at is a change in density. So if I was walking along and all of this rock was granite and it's all the same depth, there's no point in doing a gravity survey. You're not going to pick up anything. So the main things that you're seeing is that you're using your gravity survey for is a change in overburden. So overburden is the rocks at the surface that are quite weathered. It can be soil. It can be rocks that were there originally that have just been broken down. And so you can see this is an example of this orange is your overburden. So sometimes the overburden is the same thickness anywhere you go. Sometimes it increases in one direction. And then underneath this is your harder rock. And so obviously this stuff here, because it's broken down, it's the unconsolidated rocks we saw earlier, so the soils and the clays. So it's got a much lower density than this red underneath. And so that contrast that you're picking up, you're going to pick up this change. So obviously over here, you've got more high density rock, so your gravity is going to be higher. Here, you've got more of this lower density, so your gravity is going to be slightly lower. There's going to be small changes. You can also measure displacements on faults, fractures, or other structural changes. And so this is an example of one of it here, is that you can see that you've got your it's called bedrock, literally it's the bed underneath. It's at a depth, and then it's been displaced. There's a fault here, so it's moved higher up. And so do you think the gravity is higher or lower on this side compared to this side? So this again is this bedrock, this rocks. So it's higher on this side compared to this side because it's closer to this denser rock. That here it's further away and there's more of this low density stuff there. You also can use it to determine if there's an intrusion. So an intrusion is when you've got magma coming along here and it intrudes into the rocks. So this is a dike, and if it's horizontal, it's called the sill. So in South Africa, we have a hang of a lot of these in the Karoo area. So you'll get quite used to these if you do geophysics. And usually, if we go back to our rock types, they've got higher densities. So, but if this was granite and this was a dike intruded into it, it's very similar. Whereas if this is a sandstone and there's a dike intruding into it, which is the case in South Africa, you will measure this change in density. So I would expect to have a high going over this intrusion. And again, we did this on Wednesday, and you've got a body here, an ore body. If it's got a high density, then you would expect a high over it. So actually, let's draw what we would expect. So gravity, we said, would be, your gravity actually would be pretty constant there, and then it's going to go up like that. And it's constant because here there's no change. It's a flat surface. The only change is at this boundary. That's why it goes up. Here, again, it would be like that. Here, if it's a higher density, it would be like that. This one, gravity is higher on this side and decreasing that direction, and would be pretty linear. So these are the type of things you figure, but it's not this simple when you're in the field. So if we look at a sphere, that's really the main one that you deal with initially. It's really, this is all repeat, so I'll jump over it. That over here, you're going to have a different gravity, obviously, compared to over here, because here you're measuring plain rocks, here you're measuring plain rocks plus this sphere that we're calculating. But say, for example, you have a body that's not a sphere, but it's a random bush, and that's kind of what we used to in geology. Geology, you never really get nice spheres. You're usually having a weird shaped body like that. What you then do is you treat it as a small bunch of masses, and then you have to calculate the gravity for each individual point. But that is actually quite a mission, so that's why usually we approximate it to a sphere or to a rectangle, and it's much easier to put into computer programs to model it. And this is really what we're going to be focusing on. So we've spent a lot of time now talking about the Earth and the mass of the Earth and the weight of the Earth. Actually, it's these small examples that we're going to spend time on. Before we do that, let's look at units. What I'm taking now is this equation that we were using previously. We're actually not so worried about the Earth as a whole. We're looking at smaller changes in G. So that's why we're using this change in G is equal to big G change in mass. What is the change in mass between these 2 points? Actually, we can look at what's point C and point P. What's the change in mass? And then D is the depth to the sphere. So we're looking at smaller values now. And you can actually then substitute in volume back, which is kind of what we did just now. So we're looking at a change in G is equal to big G times change in M over D squared. And so now what we do is just for the M,
we convert it to density and volume.
Density is equal to mass over volume. So therefore, mass is equal to density times volume. So if we substitute that in here, we get density times volume. And we said the volume of a sphere is equal to D squared density 4 over 3 pi r cubed. Okay, and so this should actually be the change in density because we're looking at this change. So the main unit that we use is milligauss. And so you'll see that when you're calculating, we know that G is usually meters per second squared. The reason why we use milligauss is because it's looking at very small values of meter per second squared. So you literally times 10 to the minus 5 is equal to 1 milligauss. Just that you don't get confused, some textbooks use a unit called GU. And the two textbooks I actually showed you, one of them used milligauss, the other one used GU. So that's why I've included here for completeness. But really, at the moment, I just expect you guys to remember 1 milligauss is 10 to the minus 5 meters per second squared. And so all of your values you can convert into it. So in this equation above, if I put in some values here, and I calculated a 10 milligauss difference between C and P. And so it was actually 1 times 10 to the minus 6 meters per second squared. So we're looking, like I said, at very small changes in G. How much less is the value of G 1 kilometer up in the air compared to its value at the surface? Okay, and now I just want you to get some experience with the milligauss. Okay, so what the value of G 1 kilometer up in the air compared to the surface of the Earth. Actually exactly the same as the problem we did earlier. Remember, we calculated earlier that by going 1 kilometer up, there was a 0.03% change in G. That was problem 11. Take your answer from that, and that answer was in meters per second squared, and convert it for me into milligauss. So how we convert 1 milligauss is equal to 10 to the minus 5 meters per second squared. So the answer should be E. And so what you calculated earlier was that it was a 0.03% difference. Your G at 1 kilometer up was approximately, how much did you get? 9.813 meters per second squared, and at the surface was 816 meters per second squared. And so literally we're just going to take the difference between them is equal to 0.003 meters per second squared. And so this is the same as saying 3 times 10 to the minus 3. And if you want to convert it into milligauss, you've got to have 10 to the minus 5. So that's the same as saying 300 times 10 to the minus 5 meters per second squared. So it's actually equal to 300 milligauss. And this is exactly what I said earlier, that here you've got an irregular shaped body, and so you're going to break it up into these smaller components and calculate gravity from all of that. Calculate the gravity of each individual component. We've got quite nice software that allows you to do 3D surfaces. We might as well do this one because this is actually geologically relevant. Okay, so we've got a spherical cavity, so it's like a cave really, of radius 8 meters. It has a center 15 meters below the surface. If the cavity is full of water and is in rocks of density 2,400 kilograms per meters cubed, what is the maximum size of this anomaly? So, yeah, you're really just using that equation that I previously had on the board. So to calculate what G is. But when they say what is the maximum size of the anomaly, it's really what is the value of G over this, this cavity. And so easiest thing to do is to draw an image first of what they're actually asking you. So we have the Earth's surface, we have a cavity, it's got a radius of 8 meters, it's at a depth of 15 below the surface. It says it's full of water. We said water had a density of 1 gram per centimeter cubed, or 1,000 kilograms per meter cubed. And it's surrounded by rocks with a density of 2,400. Okay, so what is G at the surface here, at this point? What is G? And I was using the equation, change in G is equal to G over D squared times by density, change in density, 4 over 3 pi r cubed. And making sure your answer is in milligauss. So what, now that you've done that, would a CG5 gravimeter, so CG5 is just the name of it, be able to detect this? In theory, they can detect anomalies this small, but in reality, if there's noise, they can only detect things that small. So, would yours be able, would a gravimeter actually be able to detect this anomaly? It would. It means that you could literally, do a gravity survey over this cavity, and you would be able to pick it up. Remember we said 0.04 is how sensitive the gravity meter is. And because this anomaly is bigger than 0.04, you would probably be able to pick it up. Yeah, but theoretically it can pick up much smaller anomalies, but this is assuming no wind, no problems, no nothing. The interesting question to ask is, would the anomaly be a positive over it, or would it be a negative anomaly over it? So the thing is, it's positive like that if this body here has a higher density than the surroundings. But this body here is full of air and water, so it's got a lower density. So you actually expect it to go down. This was the other thing that we noticed on Wednesday. So we did some modeling in Grav 2DC, and we noticed the effect of depth. So what did you notice happened when the body got deeper? Did the amplitude increase or decrease as the body got deeper? Decreased, yeah. You can think of it, because we've been speaking about topography, is that the body stays here and you just get higher and higher up. And we've said already that as you get further away from the center of Earth, the gravity is decreasing. So as you're getting further away from this body, the gravity is also decreasing. So you can see here that as this body is getting deeper, that's your original anomaly, and then it goes down to this dotted one, or the dashed one, and then down to the dotted one. So, but also something to notice is that the amplitude is not only decreasing, but also the wavelength becomes very broad as it gets deeper. And so you know that it's a deeper anomaly because it's got a broader, you know it's a deeper body because it's got a broader anomaly. This is the same for a cylinder. You can see the anomaly for a cylinder is actually a bit narrower. And this is something else that we didn't look at, but you'll notice it when we do magnetics, is what is the effect of the dip. So if you've got a vertical Dyke or a vein or any body that's vertical, it's going to be symmetrical around it, but as it starts to dip, your peak moves to the bottom side of where your body is. And so you can see here, it's got quite a off-center anomaly. You can see this is much shallower, this body, than this one, and it becomes quite a sharp peak as it gets closer to the surface. So these are all just different features you can look when you're interpreting data, and you can say, oh, well, this is a very sharp anomaly, it's probably due to a shallow body, and it's a very broad anomaly, it's probably due to a deeper body. You can also model a sheet. So this is a horizontal sheet going infinitely in all directions. So the total pull at point 1 isn't infinite. So it's just saying that as you go further and further out, the pull due to these bodies on the side, on this point here, it gets so minimal that you actually stop taking it into account. There's a limited range over here that actually have an effect on this point P. But also, you actually wouldn't expect an anomaly over this. And does anyone know why you wouldn't expect an anomaly? Think of it in terms of the change in density. There's actually no change in density here, because this body is going infinitely that way, infinitely this way. So it's just going to be a flat line going over it. So it might cause a shift up and down in your anomaly, but you're actually not going to get a peak or a trough. Okay, the times that you will actually get an anomaly that you've seen already is when you've got a half sheet, and it's this edge that you're picking up. And again, you can see the shallow half sheet over here, because it's shallower, you've got quite a strong anomaly, and as it goes deeper, we said the wavelength becomes broader. So again, it applies to all bodies. And yeah, this is just density contrasts, which we dealt with a bit on Wednesday, and so it's important to note that this here is a fault in the rock, and so you've got layer 1 over here, 2 down to 2, 3, 3, and so forth. But when you're actually modeling it, do you remember that when we, in the software, we actually didn't put how many blocks? We didn't put 10 blocks in our model. We just put the one important block in our model, like that. We left the surrounding areas blank, even though there is rock in the surrounding areas. Let's see where the fault is. And what we did then is that the value we gave to this layer was the value of the density here minus the density above it. And so when we're modeling, we use density contrasts. Okay, generals. So general things to keep in mind: higher than average density bodies, so like this pink one here, it's got pluses there just to show that it's a higher density body. And the amplitude is proportional to the density excess. So all it means is that if it's got a higher density, you have a higher. Low than average density values will cause it negative, so it's going down. And you can see here it's plateaued because it's becoming this horizontal sheet that has no density contrast. This change here is just because of this boundary. It's just the boundaries that you're picking up. And that's kind of what I said here. The aerial extent of an anomaly will reflect the dimensions of the body causing it. So an anomaly will be as wide as the boundaries of the body. A sharp, high-frequency anomaly will generally indicate a shallower body. A broad, low-frequency anomaly will generally indicate a deeper body. Exactly like we said before, broad wavelength means it's deeper. The edges of the body will tend to lie under the inflection points on gravity profile. So these are your inflection points. These are general rules of thumb that you can use to find the body.